Hey, Sue.
Oh, oh, okay. Nick, can you help me to put this
That's right.
away up here? Okay,
Can you take this off, maybe?
oh, do like this. Oh, right. Then okay, there you go. And oh. And then right angle. Uh, for the later information, so later use, I would like to record your lecture. Would that be okay, Professor? I would like to record your lecture. Would that be okay?
Oh, you're asking me? Yeah, that's fine.
Oh, okay. All right, can we get started? All right, can you please stay over here? Can you please stay over here?
Professor, are you able to turn it up any louder?
Okay, that's what I'm trying to figure out. You know how to turn it louder? I try to figure it out.
You might need to, I think it's as loud as it could be on Zoom. Professor Abbott, would you say something for us?
Yeah, hello. Can you hear me? Does that work?
Oh, it's all the way up.
Can you hear me at all? Or is it just volume too
We can
low?
hear you. You're decently quiet, though.
So I'm speaking in a reasonably loud voice.
Yeah.
Check the audio settings on Zoom.
For Zoom, we turned up Zoom all the way.
No, but within the Zoom settings.
Dude, yeah. Next. Yeah. Oh. Professor Abbott, I think we're ready for you.
Okay. So you all can hear me?
Yeah.
Yeah, I see heads nodding. Okay. All right, so let's get going. So let me tell you first of all how, not completely, but what a bit about my history. I'm retired from teaching at Cal State LA, and the stuff that I used to teach when I was teaching was all kind of advanced software kinds of things. So I would teach the functional programming class. I would teach the class that I liked the most was a junior class, which was paradigms of programming or something like that. So that's kind of stuff that I used to teach, and I like that. And I never taught any AI stuff. I taught old-fashioned AI, but not the new AI, which is all the big hit these days with neural nets. And after retiring, it just kind of exploded into importance and doing amazing things and so on. So I've been following it and learning, and part of my reason for wanting to teach is that it's a way for me to learn more about what's going on. The field is changing so amazingly quickly that it's very hard to keep up. And so this course is an attempt to say, what is the current state of the art of AI, where AI means basically neural net stuff, and where is it going? Or can we even say where it's going? Can we even say how it works, which is not clear that we can. So anyway, that's kind of where I am. And I hope you're interested in this, because this is really the most important thing that's happened in computer science in a long time. So you're sort of at the ground floor, I guess. So I want mainly what I'm going to do in this class is we're going to do videos. I like videos because if you have a good video, you get a good explanation, much better than I could give you if I were just writing on the board or whatever. So we're going to do videos, but to the extent that I think that they might be a little bit difficult or confusing or whatever, I'm going to pause them every once in a while and check in with you to see if you're understanding it, if there are any questions, and I'll do a little bit of explanation if that makes sense. So you have to pardon me that I pause the video. Sometimes it's annoying when you're watching a video and someone pauses it all the time, but that's what I'm going to be doing, so I hope that's okay. Okay, so let me start, and let me start sharing. Okay, so I guess you can see this, right? My calendar. So can you all see this? No, I can't. I can hardly see you, but
Yeah, we can see.
okay. So this is a guy. He is a distinguished engineer, or I think they call him a distinguished inventor at IBM. So he does a lot of good work. He's really smart. And IBM has a series called, as you can see at the bottom, IBM Technology, which is all sorts of stuff. But they do have quite a few videos about AI. So this guy, I don't remember his name, but this is his attempt to talk about what he thinks is going to happen in AI in this coming year. Part of what I want to accomplish today is to sort of develop a common vocabulary, because I don't really know how much you know about AI and what your vocabulary is like, and what you do understand, what you don't understand. It's not that I expect you to understand a lot, but I don't want to bore you with stuff that you already know. So let me ask you first of all, and I'm going to have to look at this little window. Have you all used ChatGPT? Raise your hand if you have. Raise your hand. Yeah. Okay. So most people have. And it's very hard to see in this little window, but that's good. So you all know that there is a big deal about AI and large language models, which is what ChatGPT is based on. And so most of the stuff we'll be talking about is based on that technology. So let's see what he has to say. The introduction here is he made predictions last year, and he's reviewing his predictions, but we're going to skip over that. So this is what he has to say for this year.
Professor, we can't hear your stream. It would be on this side. You think so? Should be able to share audio whenever he shares the screen.
Professor, can you hear me?
Yes,
I think you might need to share the audio on your stream. We can't hear anything.
you can't hear anything. What do I have to do to share the audio?
You see the tab where Zoom has the share screen options?
I see the share screen, yeah.
If you click on the little tab, it'll bring up a list of menus and you'll see one of them says share audio. You just click that and. Be good.
Well, all the way on the left, it says audio, it doesn't say share audio, and then it gives me select a microphone, which is, you know, the microphone for my computer, and select a speaker. Test speaker and microphone.
Oh, not in the
Switch.
settings, not in the settings, in the, should be on your desktop, so if you click back where on the video was, where your screen sharing. There should be a little Zoom tab that's showing you that you're sharing your screen at like the top of your desktop, or the top of your monitor. You see, there's like a little red tab.
So in the Zoom window,
Oh, is it? Yeah. I don't know.
What is it? It's a,
On his side, he has to click on it. And then share screen option this one? Yeah, click on the carrot, see if it comes up.
This is us here. That's called.
Advanced sharing option.
This is just us though, this isn't him. Yeah. Well, we could just load up the video on our side.
so you can hear me when I'm talking, but you can't hear the video?
Yeah. we can hear your microphone input. We can't hear any of the computer's audio.
Oh, okay. Let me try something. Okay.
An AI agent can break down complex problems to create multi.
Is that better? Did you hear that?
Yeah.
Yes, no?
Yes.
plans, and it can interact with tools and databases to achieve goals.
Do you hear him talking now?
Yep.
Is that a yes? So when I start the video, do you hear him talking?
Yes, Professor, we hear him talking.
Okay, so we'll just do that.
I think most people are on board with the utility of a well-performing AI agent. Trouble is, today's models, well, they struggle with consistent logical reasoning. They can usually execute simple plans, but when it comes to handling complex scenarios with multiple variables, they often lose track and they make decisions that don't quite add up. So we'll need better models in 2025. Speaking of which, trend number 2 is inference time compute. Now,
Okay, so let me stop here. I apologize. So how many of you know the word agentic? Are you familiar with that term? And again, I can hardly see you because I'm sharing my screen. I just see this little window where I see the whole room, but I really can't see you. So how many of you know the term agentic? Have you heard of this?
No.
No?
No. Yes.
Okay, so ChatGPT has been around for a few years, and the big deal these days is what's called AI agents. And to refer to the field of AI agents, the term that they use these days is agentic. So agentic means about agents. That's all it means, but you hear it all the time. So, you know, if you do AI stuff, you'll hear the term agentic. And agents are sort of a somewhat advanced version of things like ChatGPT. So as he said, an agent is something that can more or less act on its own. You give it instructions, you may give it access to resources like your computer or the internet or whatever. You give it a goal to try to achieve, and then you say, go do it. And it does what it does. It tries to do it. So that's what agentic AI is, and that's what people are thinking is going to be the big, at least economic development for this coming year. It's not particularly theoretical advance. There's no big deal in terms of what agents can do that ChatGPT doesn't, but it's the big new use for AI. Okay, does that make sense?
Yeah.
It's hard for me to tell whether you understand what I'm saying.
Yes, Professor, that makes sense.
So is there anyone, Nick or Sue, could you be an intermediary if I say, do you all understand? And you see what people, what they're saying, yes or no, nodding their heads, and then you tell me through the speaker that I can hear Nick pretty well.
Sure, Professor, I can relay that to you. Did you hear that?
I heard it, but wasn't very clear.
I can relay that to you, Professor.
Is there anyone who's close to the microphone? That would be better.
Professor, I'm the closest person.
Yeah,
Yes, that'd be okay if you just stand,
Right there?
yes, stand in the front. Okay, there you go.
Professor, how does this sound?
Yeah, that's better.
Okay.
Oh,
Okay.
Let me remove my stuff so they can sit on the. There you go. Sit on it. Okay, right?
Okay, so let's move on to this inference time compute. So first of all, the term compute seems to have become very popular in, because of AI. And compute means the effort of computing, basically, running your computer. But it's sort of a noun that refers to the kind of the amount of computing you do. So inference time computing, he'll probably tell you. So let's watch what he says.
Now, during inference, an AI model goes to work on real-time data, comparing the user's query with information processed during training and stored in its weights. Newer AI models are extending inference processing to essentially spend some time thinking before giving you an answer. And the amount of time it spends thinking is variable based on how much reasoning it needs to do. So a simple request that might take a second or two, or something larger and harder might take several minutes. And what makes inference time compute models interesting is the inference reasoning is something that can be tuned and improved without having to train and tweak the underlying model. So there are now two places in the development of an LLM where reasoning can be improved: at training time with better quality training data, but now also at inference time with better chain of thought training, which could ultimately lead to smarter AI agents. All right.
Okay, so you're all familiar, I imagine, with the idea that when you have a neural net, it really doesn't do anything until it's trained, right? You all know that?
Yeah, we're familiar with that.
And that training neural nets involve a lot of computation, a lot of compute, as they say, and it can be very expensive. The amount of money spent on training the underlying mechanism for ChatGPT was, I don't remember, hundreds of millions of dollars. I mean, it's really a lot of money. And so the training is one aspect of what you do when you build an AI. Once it's built, you have this system, and a neural, we'll see later, but a neural net is a system that has a bunch of things set, parameters they call it, things set, and then you interact with it. And ChatGPT is something you interact with. And when you interact with it, it responds pretty much immediately, right? When you give ChatGPT a prompt, you get an answer back, instantly. So what this is talking about is that there are now ways of letting the system think a little bit before responding. And that is a significant advance in the theory and technology of AI. And so this is one of the things that is going to be very important this coming year. Inference time compute, and it's also called test time compute, because the distinction is between training time, the time that you spend when you're training the neural net, and the time that you test it. And testing is, you give it a prompt and you see what it answers. And that's if you're an AI developer. But inference time compute is essentially the computing during the same time as it's responding to a prompt, but you're not testing it anymore. A user is just interacting with it.
Trend number 3 is very large models. Large language models consist of many parameters which are refined over the training process. Now, the frontier models in 2024, they're in the range of like 1 to 2 trillion parameters in size. The next generation of models are expected to be many times larger than that, perhaps upwards of 50 trillion parameters. But if 2025 is the year of enormous models, it may also be the year of number 4, very small models. Models that are only a few billion parameters in size. And yet you don't hear the phrase only a few billion very often, but there you go. And these models, they don't need huge data centers loaded with stacks of GPUs to operate. They can run on your laptop or even on your phone. Actually, I have the 2 billion parameter IBM Granite 3 model running on my laptop, and my device doesn't even have to break a sweat to run it. So expect to see more models of this size tuned to complete specific tasks without requiring large compute overhead. Now, do you know what the most common enterprise use cases were for?
Okay, so I was hoping this would stay up, but his number 3 is very large models, and there's some dispute about that. It had been thought for a while that the larger the model, the more parameters in the model, the better the system would get. And that has been kind of disappointing. It was true for a while. It was true when we went from ChatGPT or GPT-2 to GPT-3 to GPT-4. Each one of them got significantly better than the previous. But going from GPT-4 to GPT-5, which is what the next step would be, doesn't seem to be adding that much in terms of the capability of the system. So I'm not sure that very large models are going to be a big deal in this coming year. Very small models really are, because if you have a small model, it can run a lot faster, it takes a lot less computational power. And so the very small models are important. Very large models, I would say, are not all that important, but then, we're different people.
For AI in 2024? Well, according to a Harris poll, it's improving customer experience, IT operations and automation, virtual assistants, and cybersecurity. Looking ahead to 2025, we will see more advanced use cases. So think customer service bots that can actually solve complex problems instead of just routing tickets, or think about AI systems that can proactively optimize entire IT networks, or think about security tools that can adapt to new threats in real time. Now, when I first used generative AI back in the day to help me build a beer recipe, the context window for that LLM was a mere 2,000 tokens. And today's models have context windows measured in the hundreds of thousands or even the millions of tokens.
Caught him with his mouth open. Do you know what a context window is?
Yes.
Go ahead. What do you think?
Context window is basically how much an AI can have in their system prompt, and basically give instructions based on that.
Nah, I didn't hear that well enough to
It's a
know. How much?
He was essentially saying the context window is how much can be within an AI agent's prompt when. What do you think of that, Professor?
How much? Say it again?
How much what?
Say,
Basically, how many tokens can be used in a prompt to give instructions to a large language model?
something like that, yeah. So if you're interacting with, say, ChatGPT, and you give it a prompt and it gives you a response, and you say, no, I didn't mean quite that, I meant that, this other thing, or something like the previous one. In order for that to work, it has to know what the previous one was. It has to have a memory of some sort. And so all the stuff that it can remember during an interaction is the context window. And so the question is, how big is that context window? How much stuff can it remember from the current conversation? And as he said, these context windows started off pretty small and they're getting larger and larger.
We are getting close to number 6, near infinite memory, where chatbots can keep everything they know about us in memory at all times. We'll soon be in the era of customer service chatbots that can recall every conversation it has ever had with us, which hopefully we'll consider a good thing. Okay.
So let's assume that's true. So you interact with ChatGPT, and then you go away and you come back the next day and you start up interacting with it again. As I'm sure you know, it doesn't remember what you did the last time. Now, what he's suggesting is that with these very large context windows, which they can store for one person or another person separately, it can remember its whole history with you. And he says, well, is that a good idea or not? Do you want it to do that? But that's what this number 6 prediction is all about. Okay, he has 2 more predictions, but they're not very clear. And so I don't really want to spend time on them. I want to go on to the next video. So any question about these? Anything you want to say?
Professor, I think we're good on questions.
Okay. So is this consistent with your sense of what AI systems are like? Is it all mysterious? Is it all something that you already know and it feels trivial? Is this about the right level that, we're kind of starting at?
Serious? Guys, can I see a show of hands? If you think it's trivial, put your hand up. Okay. Like, simple or easy.
I mean, there hasn't been much technical stuff, but just the concepts.
Nobody put their hand up, Professor, so no worries.
Okay. So you all, if I'd asked you before we started, what's the difference between inference time compute and training time compute, would you all have been able to say that?
Definitely not.
And would you all have been able to say what a near infinite context window is?
Also, definitely not.
Okay, so the point of these introductory videos, these starting off videos, is to try to establish a level that we all understand. And I'm glad to find out that this is, at least some of it is new to you. So I want to go on. Anyone watch her videos? You recognize her? Her name is Sabina Hassenfelder.
Nope.
No, I like her a lot. She's a theoretical physicist, and she stopped doing theoretical physics, although she remembers it all, and has become a YouTuber and makes YouTube videos about science stuff. So this video is her version of answering this question. So you all see what this question says?
Yep.
That's part of the screen, right?
Yep.
Can someone tell me what that means?
Does anybody know what AGI means?
That's the question, yeah. What does AGI mean?
Artificial general intelligence.
And what does that mean?
Basically having, like what you think of, iRobot, right? So an AI that can, create, creative thoughts of its own without using any other source, basically being able to compute its own thoughts and, iRobot, yeah, you all watched the movie, yeah. Seemingly human intelligence, yeah.
Did you get that, Professor?
Sort of.
Essentially robots that can have their own thoughts and are intelligent on their own.
So AGI doesn't necessarily refer to robots. Is that what you were saying?
That is the mind.
It's just they're saying just the mind aspect.
Yeah, just the mind aspect. So the idea, I mean, artificial general intelligence is the idea that you could have an artificial, a neural net that can think about anything that humans can think about and do it as well as humans. So that's what artificial general intelligence is. And there's also the term ASI, which stands for, anyone know ASI?
Anybody? We don't know, Professor.
No, okay. ASI stands for artificial superintelligence. So ASI would be a system that's smarter than the whole world put together, something like that. So are we on the brink even of artificial general intelligence or even artificial superintelligence? Some people think so, and we'll see some of that. So that's the question she wants to talk about.
Close are we to artificial general intelligence, AGI for short? At the end of last year, OpenAI announced their newest model, O3. That caused quite some buzz and a lot of speculation that we're close to machines with human-level intelligence. If you trust YouTubers, which maybe, just maybe you shouldn't, O3 is AGI. Let's have a look. The newest OpenAI model impressed with several test scores. First, there is a test with hard maths problems called Epoch AI Frontier Math. It'll probably take me a year or so to figure out what the questions even mean. So far, the best an AI did on this test was to correctly solve 2% of the problems. O3 managed a whopping 25%. The second impressive feature is that it produces code faster and with less compute, so at a lower cost than previous models.
So for an order of magnitude more speed and cost, we can deliver the same code performance on the deep
Or even better.
or even better.
If you're a software developer, this is either very good news or very bad news. And
You've heard of that? Software being generated by AI?
Anybody heard of that? Yeah, we've heard of that.
Okay. So question is are AI systems going to put you all out of work?
No,
And there's a lot of debate about that. Are they going to get good enough so that no one needs any human programmers? Or will it always be the case that no matter how useful the code is that these, AI assistants generate, you'll need human programmers to check them out, to see if they, if the code makes any sense with respect to what the problem is. Well, a lot of stuff. So you will need human programmers. But that's an issue. And one of the most successful applications so far of AI has been coding assistance. So a lot of people think, a lot of programmers think that it makes them a lot more productive. So like Microsoft has what they call copilots, and GitHub has its own version, which may be the Microsoft one. Anyways, there are a whole bunch of these AI assistants for programming, and that's one of the major fields that's under development, and we're going to devote more time to it later. It's an important area.
The third test score, which has attracted most of the attention, is O3's performance on a test called ARC-AGI. That stands for Abstract and Reasoning Corpus for Artificial General Intelligence. It's made of graphical puzzles. Here is an example of an input and an output, another one, and another one. And then here is the question. You can
Okay, can you solve that problem? Now it's telling you that if this is the input, the output should be this. If this is the input, the output should be this. If this is the input, the output should be this. Here's another input. What should the output be?
Blue. They say a blue cross.
Blue cross, like these blue crosses?
Yep.
It's gonna be.
I would say that's half right.
Fine. Great.
I notice the difference between these figures and these figures. I mean, this one, for example, there are 3 of these. And here there's only one, but it's, you know, takes up the whole grid. So you expect here, there would be one blue cross, as you said, but it would be big. It would take up the entire grid. Okay, so the question is, how did you decide that that's what the answer should be?
Somebody said pattern recognition.
Well, I mean, yeah, but what does that mean? More concretely, how did you decide that that was what the answer should be? Can you give me the rule
You go ahead.
that lets you take the input and determine what the output is?
Chosen, there's more of, so for the blue squares, there's more blue squares than there are two red shapes than.
Professor, somebody said that they're taking the shape that occurs the most within the picture.
I think that's right. So as you noticed, there are 3 of these blue things and only 2 of these red things, so it's the blue thing that gets reproduced down here. In this case, there are 3 red ones, 1 blue one, and 2 green ones, but 3, there are more of these red things than anything else, so it's the red thing that gets reproduced. In this case, there are more yellow things than blue or red, so it's the yellow thing that gets reproduced. In this case, there are more blue things than whatever that color is, and so the blue thing is one that gets reproduced and expanded. Okay, so that's the rule. At least I would say that's the rule. I'm pretty sure that that's correct. Now, why is that difficult to do? The point of this test, this is, you know, the ARC-AGI test that this guy, Francois Collet, made up. And the test has a whole bunch of these things. The point of this test is that he thinks that human beings can do these kinds of puzzles, and computers have a hard time with them. Why do you think that's the case? And it's the true. I mean, when you test computers on these same puzzles, they don't do very well. Why is it that humans can do it and, you know, AIs, as we currently have them, can't?
What was that?
The centuries of evolution.
Somebody said centuries of evolution.
No. I mean, that may be true, but what is it about these problems that make them hard for computers and easier for people?
Anybody else have any ideas?
I would say could it be it's too abstract for a computer to decipher what's going on, and like a human would be like, okay, based on these patterns, like give me what's the most reasonable outcome, right? So I would say like abstraction in a way.
Yeah, somebody said it's too abstract for a computer. That he said that they're struggling with the abstraction. It's something that humans are better at.
I AI, I mean, the point of AI is that it can abstract from examples to get some sort of general idea. So AI vision is, image recognition. You give it a whole bunch of pictures of dogs and elephants and tables and, all sorts of stuff. And all the dog pictures are different dogs, all the tables are different tables and so on. And these image systems are good enough so that you give it a new picture of a car or table or dog or whatever, it's able to say that's a dog or that's a table. So it can abstract away from concrete examples and in some sets generalize that so that it can recognize another instance of that category. So the point of AI is that it does, in some sense, do abstraction. That's really the challenge.
Did you want to share one too?
I think in this example, it's probably looking for a rule. So in the first three, it's more than 3 shapes. So the last one might trip it up because the computer tries to find like a rule to base off like speech.
Somebody said that the machine is looking for rules that it can use to decide. And so one rule that you might see is that certain patterns occur more than 3 times, but in the last one, it only occurs twice, so it might throw it off.
I would say that's close. Now, you're right that what it has to do is find the rule. What is the rule that gets you from here to here, here to here, here to here, that you can apply to this one to get you an answer? And the answer is what we came up with. You take the pattern, the figure that occurs more than any of the others and blow that one up. Okay, so that's the rule. So and if you gave the system a whole bunch of examples like this, where that's the rule you'd want it to apply, eventually it would learn that rule. So it's not that the rule is so hard. What's difficult is to even realize that what you have to do is count the number of instances of each of these different figures. If you look at them, my inclination would be to look at the figures and say, well, these figures are different. Like here we have five blue squares, and here we have 5 red squares, but they're in a different pattern. So these are sort of symmetric and this is not symmetric. And you might say, well, if it's a symmetric pattern, then you copy it down here. If it's not symmetric, you don't. Okay, but that doesn't work here because this is a symmetric pattern, this is not symmetric. And the green one is, well, the green one's kind of symmetric. But it's the non-symmetric one you copy down here. In this case, what is it? In this case, it's the pattern that has the fewest elements, I think. So the yellow patterns have only 4 elements, whereas the blue and the red have more than 4 elements. So maybe that's what we should be looking for. Okay, so the problem is you don't even know what to look for in coming up with a rule. And that's what people are better at than computers. If computer says, I don't know, what should I even think about? What should I consider as a possible base for the rule? And, people can do that. You guys did it. Whereas AI systems are not good at that. They're not good at just sort of taking sort of the world as it's presented to them and saying, oh, here is something important about the world, or here's something else that's important about the world. So that's why it's easier for people to do these kinds of problems than for AIs. And that's a really interesting thing. And the guy who figured this out, this Francois, whatever his name is, I think did a real service in coming up with that.
Almost certainly solve this, and if not, the problem is probably your glasses and not your brain. Yet AI struggles with inferring the logic behind these questions. Before the O3 announcement, the record holder for this test scored about 55%. O3 scored 75% at low compute and 87% at high compute. They
Okay, so sorry to interrupt again. She's been talking about O3 all along. Do you know what O3 is?
Large, latest.
Would you tell us, Professor?
Well, if you don't know, I will, sure. But
Somebody
maybe
said
no.
it's an OpenAI model.
It's an OpenAI model, that's correct. So the previous series of OpenAI models have been like, as I said, GPT-2, GPT-3, 3.5, GPT-4, and now this is GPT-01, or, down here is 01, and here's 03. So why is it so different? It's really a different architecture in some sense. And so O3 is the newest, best thing in this new architecture. And the new architecture are systems that, as we talked about before, are systems that think before they respond. Okay, so there are only two of them, O1 and O3. There's no O2. But both of these think in some sense, they take time before they come up with an answer. Whereas all the previous AI systems have answered instantly. Okay, so that's what we're talking about here. And it turns out that development, being able to build a system that has time to think and actually does something useful with that time, makes these systems a lot more powerful.
They pay the price for that, literally. The high compute version costs as much as $30,000 for a single task, whereas the previous model may do with a few dollars. Speaking of cost, the Chinese firm DeepSeek just released a new open source model that has a similar performance to GPT-4. It was vastly cheaper, but has an interesting identity problem.
Now, I've been testing it out this morning, and on the surface, it looks and acts just like OpenAI's ChatGPT. And in fact, it actually thinks it is ChatGPT. When I asked, what model are you? It answered, I'm an AI language model created by OpenAI, specifically based on the GPT-4 architecture.
But back to O3. On the technical...
Okay, so, what was I gonna say? Now I don't remember.
Aside, the biggest advancement of O3 is that it internally produces several possible solution paths and then evaluates them. This is called a chain of thought. It can even keep track of which solution strategies work best. The high score on the ARC test attracted attention because the average human score on this test is roughly 76%, so that's comparable to the O3 performance. But it's not like passing this test means you have an AGI. It's that if you have an AGI, it should pass the test. So no, this result does not tell us that O3 is AGI. Still, Stephen Heidel from OpenAI commented on X Twitter that it's beginning to look a lot like AGI. Part of the problem is that we don't have any good definition for what AGI even means. Indeed, Sam Altman, the CEO of OpenAI, says he doesn't like the term, but he thinks that by the end of 2025, machines will outsmart humans in many ways.
People would be sad.
Okay, so I remember what I was gonna say. You remember when she talked about briefly this thing called DeepSeek? DeepSeek, where is it? There it is. DeepSeek. Have you heard of DeepSeek?
Nope.
Anyone know what DeepSeek is?
You want to go ahead?
Well, it's made by China and it's an open source model. It's kind of on the same premise as O1, but they do it a different way. But it's been competing with O1 performance, especially like recently, like 2 days ago.
Somebody said it's a model you said it's trained a little differently than?
Yeah, but it has comparable performance to O1.
Somebody said it's a model trained a little bit differently than O1, but it's got comparable performance, made in China.
and it's made in China. That's the big deal about it. So far, before DeepSeek, people thought, well, the US companies are far ahead of the Chinese companies. And then DeepSeek came out with its, first of all, they came out with a version called V3, which was sort of like GPT-4. And then they came out with something called R1, which is like O1. And what is amazing is that, first of all, it's as powerful as our systems. And secondly, it's even cheaper. It's a lot cheaper to run. So the Chinese have done a lot. And the company that makes this is very well respected. The people who work there, the people in the US who know the people who work there or know about them, have a lot of respect for those people. They say they're very good. So that's DeepSeek. Now, where are we? There we go. Come on.
By the end of 2025, machines will outsmart humans in many ways.
People would be sad if I didn't ask you. We hear a lot about artificial general intelligence. What is it? When is it going to happen? And what will be the implications?
It used to be a term that people used a lot, and it was this really smart AI that was very far off in the future.
Yeah.
As we get closer to it, I think it's become a less useful term. People use it to mean very different things. Some people use it to mean something that's not that different than O1, and some people use it to mean true super intelligence, something smarter than like all of humanity put together. But I will say, by the end of next year, end of 25, I expect we will have systems that can do truly astonishing cognitive tasks, like where you'll use it and be like, that thing is smarter than me at a lot of hard problems.
Though the reason he doesn't like talking about AGI may be that OpenAI has a lucrative deal with Microsoft that, however, has a clause saying the contract will terminate if OpenAI reaches AGI. They did this in 2019 to prevent commercial abuse of the technology because safety and all, but come 2024, they prefer removing the clause because fuck safety. Personally, I strongly doubt that OpenAI will make it to AGI anytime soon, if ever. It's because the test results alone don't tell the full story. O3 is still a specific type of AI called a large language model that's trained on a lot of data with examples of the problems it's supposed to solve. But most humans can solve the ARC problems without having ever seen anything like it before. This tells us that these models are not remotely comparable to human intelligence. Many in the AI business currently think that large language models will scale with more data. That is, the more data you feed into them, the better they'll get, eventually surpassing human intelligence. This scaling hypothesis has been observed in many previous models. However, as we just discussed in an earlier episode, there are indications that progress on LLMs has slowed down and that these models will not continue to scale. Yann LeCun from Meta is among those who think that large language models are not the way to AGI, and he thinks it won't come before the end of the decade.
So that's what we talked about before, when the IBM guy said we're 2025 may very well have super large models. And, that seems really, so far, it seems that won't solve the problem of making the systems a lot smarter.
We have LLMs that can pass the bar exam, so they must be smart. But then they can't learn to drive in 20 hours like any 17-year-old. They can't learn to clear up the dinner table and clear up the dishwasher like any 10-year-old can learn in one shot. Why is that? What are we missing? What type of learning or reasoning architecture or whatever are we missing? It's not going to happen next year. Like you might have heard from
from, you know, some other folks.
Sam
like, you know,
Altman, yeah, right, yeah.
Sam Altman, you know, Elon Musk, you know, various people, or, you know, Dario Amodei, yeah, it's gonna happen within the next 2 years or something. No, what may happen in the next 2 years is that it's gonna be more and more difficult to find cases where common people will be able to ask questions to the latest chatbot that the chatbot would not be able to answer.
Gary Marcus, a cognitive scientist who's worked on the emergence of intelligence, also thinks that AGI is much harder to achieve than many in the field presently believe, and that the problem is made worse by the intellectual monoculture of Silicon Valley.
AI.
So do you recognize the guy who was here before, that Jan LeCun? You know who he is?
We don't, Professor.
No? Okay. So he is the head of AI for Meta, you know, Facebook. He also teaches at NYU. And he's, if you could, you know, hear him well enough, he's French, or he comes from France, he has a French accent. And I have a lot of respect for him. I think he's very good. You all recognize Sam Altman, the guy who was speaking before?
Does anybody recognize Sam Altman? A couple people do.
Okay, so Sam Altman is the head of OpenAI, and he tends to be a little bit slippery. You know, he comes off as a kind of modest guy, but behind your back, you're not quite sure what he's going to do. Okay, so this is Gary Marcus, who is not a computer scientist. He's a psychologist or psychology professor, retired psychology professor. And he's been saying for a long time that he doesn't think that we're very close to AGI.
It's harder than its originators realized. And actually, I should have added, it's harder than most of the people who are hyping the field right now realize, which includes CEOs of companies like OpenAI, not to mention any names. We have an intellectual monoculture in which almost all of the research dollars and energy goes towards transformer models and almost nothing else. And that's insane.
But OpenAI and Anthropic and others have spent hundreds of millions of dollars to train these models. They can't just start over again. It's too expensive. This makes it easy to predict what will happen next. These companies will quietly drop the AGI idea and instead find niches in which their models perform well enough to be profitable. Indeed, according to Business Insider, in internal documents between Microsoft and OpenAI, they define AGI as any system that will make more than $100 billion in profit. If I now tell you that OpenAI also considers putting adverts on its models, it suddenly all makes sense. General intelligence means spamming your customers with ads. The future will be bright. Artificial intelligence is everywhere.
Okay, that's the end. The rest of this video is an ad for something that she's selling. So, up to 7 o'clock, I think I don't want to show you any more of these videos at this point. But what I'd like to do is go over the syllabus. So first of all, let me show you where it is. So I'm going to use, we're going to use Discord as a communication channel. And so you all ought to get a Discord, you know, or join this Discord. And one of the things you'll find is if you go here to resources under information, this points to this syllabus. So if you want to find it, you can get it there. Okay, so let me go back to the syllabus. So there's a lot of stuff in this syllabus. So let me show you quickly what's here. First of all, a couple of big or three big questions that I think you should keep in mind that, that we really don't have solid answers for with respect to AI. So keep these three questions in mind as we go through the semester. Second thing is Substacks. And Substacks are like blogs, and they're the currently popular way of doing blog things. And the two that I think are the most useful for us anyway are one by Gary Marcus, the guy we just saw, and another one by Tim Lee, who is a science writer, and he writes for the general public, and he explains how AI systems work. So he does good things. There are a lot of YouTube channels that have good stuff for us. One we're going to use a lot, especially in the first few weeks, is 3 Blue, 1 Brown. How many of you are familiar with 3 Blue, 1 Brown?
A couple people are.
Okay, good. So I think it's very good. And the guy who does it, Grant Sanderson, is very smart. He does the 3 Blue, 1 Brown videos are about science and math topics in general, but he has a series on AI and neural nets. And so these are the AI videos that he does. Then there are a bunch of others which I don't have much detail about. So one by this guy, Adam Luchek, and one by AJ Halthor called Code Emporium. Aryan Codes is a Substack about Python. It's not about AI. Small set of videos, which are pretty good. DeepLearning.ai is a company that does online courses, and they're free online courses. So they have lots and lots of courses, and they're all basically well done, and they don't require a whole lot of background. So you should look at them sometime, and this is a very good resource. IBM Technology, we saw that video. Letitia is a woman who makes videos about stuff. She tends to be more mathematical. Serrano Academy is a guy who makes very intuitive videos. So they're pretty easy to follow. So he's pretty good. He describes himself as, we use illustrations, analogies, and cartoons to demystify and capture the essence of topics in machine learning and mathematics. Now, he has one video, this one, which is not about AI, but it's a personal story, and you might enjoy it. This guy, Steve Seitz, makes videos about computer science and AI, and all his videos are about 5 minutes. So they're really short, and he does a really good job of getting a lot of good information at an intuitive level into his videos. This one, Vizura, is an organization that was started by people from India who all of them have advanced degrees. And we're going to look at one of them later today. Guy who has a PhD from MIT. And these people got together and created this company as a way of teaching about AI to Indian students or the Indian public. So they try to make it as intuitive as possible. And the one we're going to look at, I think, is very good. Others that I've looked at are not quite so good, but anyway, there they are. So this is a good website. And the last one in my list here is Wes Roth, who sort of delivers the news about AI and new developments. And he does a good job of that. He knows what's going on. He's not so much a technical guy, but he knows enough to understand what's important, what's not important, and to know how to talk about it. And I have a lot of pointers to his videos. Software resources, Hugging Face. Have you heard about Hugging Face?
Has anybody heard about Hugging Face?
Yep.
Just a couple people.
Okay, it's a great resource for AI systems. LangChain is somewhat similar, although it has more specific focus. So these two are really great software resources. Wikipedia's page on generative artificial intelligence, which is what LLMs are. It's a pretty decent page. And down at the bottom of the page, there's a box. If you know how Wikipedia works, it has categories. And at the bottom of this page, it has a whole bunch of AI categories, and it shows you what they are and the pages that are in the various categories. Okay, so to do, I want you all to join Discord, the one that we looked at. Now, the main work that you're going to be doing, at least one part of the main work, is to make videos. So I want you guys to make videos. So as it says, I want everyone in the class to establish their own YouTube channel. You'll upload your videos to this channel, and this post tells you about doing that stuff. So those will be homeworks. There won't be any Canvas submissions. This will essentially be your homework, making videos. Also, your YouTube channel will be your face to the world. So I really recommend that you try to make it look good. Make these videos look professional and make it something you can be proud of so that when you apply for a job, you can show off your videos. Okay, so what are your videos going to be about? Each week, we're going to explore some area of AI. Your video will discuss the topics of the week. And I don't want you to make long videos. You know, a lot of the videos are at least 20 minutes long. I'm suggesting you make videos that are 10 to 15 minutes long. Now, there's a system called Notebook LM that I want to show you. And the Discord, just maybe we don't have time to look at, but anyway, the Discord post illustrates some of its power. And that's what we were looking at before. So this post. So this tells you how you can use Notebook LM to get information out of this video that we just looked at. So we just looked at this Sabine Hassenfelder video about AGI, and you can use Notebook LM to summarize a lot of video or organize a lot of that information. It's very powerful and it's a very nice system. So I strongly recommend that you use it, although it's not required. Okay, so what kind of videos will you make? I recommend that you take seriously the idea of making good videos. That's the homework for this class. Make videos. So instead of doing programming or instead of writing papers or any of that stuff, the homework will be to make videos. So take this as an opportunity. This is an opportunity to develop your video making skills. So think about what are good videos. What are videos that you like? And what makes them good? What makes them attractive and engaging? Can you make videos that are similarly attractive and engaging? So in order to do that, you'll probably want to use video editing software. And I'm not assuming you know anything about video editing software. I suggest you start learning about it. So if you do a search, and this links to a search for best free video editing software for 2025, you get lots and lots of references to free video editing software. And so if you make videos using video editing software, you know, that will be a way of learning about how to make good videos. This article talks about half a dozen of these, and the half a dozen that it talks about are the ones that you find in all the lists of the best. So this is a good place to start. Now there's another system called Manum, which is what 3Blue1Brown uses, and this was written by Grant Sanderson, who does this 3Blue1Brown. It's an amazing graphics library. There's this other graphics library, which is desmos.com, which we'll see in the second half of today, which is good for doing mathematical demonstrations. And there's a third website called napkin.ai that lets you give it text and it gives you visuals. So it's something like, what is it? DALL-E, where you give it a text, you say, show me, make up a picture, make up an image of something or other. So this isn't quite the same. You say, I want to make let's say I want to make a PowerPoint about this topic and give me some visuals for that. And it'll come up with something which may or may not be useful. So this may be useful to you. And so as I say, your efforts to use video editing software will be taken into consideration when your videos are being evaluated. And we understand that the initial results can be rocky as you learn new software, but I strongly urge you to try to learn how to make good videos. You don't have to, it's not an assignment. So on the other hand, it's acceptable, although boring, if your videos are Zoom recordings of slide-based presentations. And if you do that, your video should be about 5 slides long, not counting the title slide. So come up with 5 slides that are decent slides. So the person who's going to be looking at your videos and evaluating them is Nick. So Nick, do you want to say something about this? And
Yeah.
how do you think about this?
I'll be evaluating your videos mostly on professionalism, clarity, how knowledgeable you are, how well put together it is, things of that sort. Yeah. Is there more you'd like me to elaborate, Professor Abbott?
No, just whatever you want to say.
Yeah, sure.
Okay, that's it.
Yeah.
Oh, okay, so Nick is an important person to you. So this is the weekly schedule, and I'm not going to go through week by week, but you can look at it. You can see the first, it's in 2 parts. Let me show you that. So the first part is Introduction to AI, to Python, Neural Nets, and LLMs. Not much Python, but Introduction to Neural Nets and LLMs. And that's the first 6 weeks. And the weeks are, each week is divided into primary materials, which are the videos, and they're almost all videos that I want you to base your base your videos on. And these are supplemental videos that you might be interested in. And you can also include stuff about these in your in the videos that you make. But the most important stuff, the stuff that the week is about, will be the primary materials. And haven't divided all these weeks into primary and non-primary yet, so I still have to do that. But by the time we get there, I'll have done that. And then the second part of the class from week 8 until the end are different topics in AI and relevant issues. So coding assistance, which, as I said, is a very important area. AI and natural science, I hope you know that Demis Hassabis of DeepMind got a Nobel Prize in chemistry for the system AlphaFold that predicts how proteins fold. And he has a nice Nobel talk about that. This week is about critiques of LLMs. As Jan LeCun said, he doesn't believe LLMs are the answer to AGI. Gary Marcus says they're not the answer to AGI. Francois Chollet is the guy who has these pattern recognition things. So he has a talk, and there are a whole bunch of talks about why LLMs are not the final answer to AGI. This week we talk about human intelligence. And this woman, Ev Fedorenko, who's at MIT, looks at how language and thought interact. And the summary of what she says is this. I don't have it written down here, but what she says is that language is neither necessary nor sufficient for thinking, which is kind of surprising. So what the AI systems that we built so far do is they do a whole lot of good work with language, but that's not how we think, according to her research. And so is there any reason really to expect that if we get our LLMs to be even better, that they'll be able to think better? Well, maybe not. So what are the other opportunities? What are the other approaches? Well, the other approaches are O1 and O3. So how do those work? And Google has its own version, Gemini, Flash, and there's some others, and there are other ways of other directions to move. So these talk about that stuff. Now we want to talk about how these reasoning models work. And so this week will be about that. How do they really work, to the extent that we know how they work? And what are some of these general purpose tools? NotebookLM, I said, is really terrific. AI Studio is good. Canvas is good. Anthropic has a system. Its chatbot is called Claude, and it has a system called Computer Use, where you give the computer instructions about their system, this computer use system, instructions about what you want it to do, like I don't know what, sort your file system or something. You just give it instructions and it'll go ahead and do it. It's sort of an advanced version of an AI agent. This is really interesting, a meta prompt to create prompts. One of the big deals in using AI is coming up with good prompts. And so a field these days is called prompt engineering, and people now get jobs because they're good at coming up with prompts for chatbots. I don't think that has a future, but anyway, that's what people talk about, prompt engineering, a lot. So one guy said, I'm going to write a prompt that if you just kind of fill in the blanks, you can get give you the response that you want to any subject matter. So this is really interesting, what he came up with. And then finally, today and tomorrow, Stuart Russell is the co-author of the AI book. He has a talk about where we're going with AI. We don't talk about ethics in here at all. This is the only talk that talks about ethics. And it's not mainly about ethics, but he says, what should we want what should we want as a future AI? And he makes a good point, and he has a really good idea. So anyway, I like his idea, and that's the end. So now the other thing that we're going to do, or you're going to do, is a project. So Sue is going to be sort of the project coordinator. And there's this whole list of project ideas, goes on. And you're going to be asked to form teams and work in teams of like 4 or 5 people on a project. And we'll get together, Sue and I will get together with the teams week by week. And depending upon how many teams there are, we'll be able to meet with each team. One of us will be able to meet with each team maybe every other week. If there are fewer teams, then maybe we could do it every week, or maybe we could work together on a team or whatever. So we'll have to figure out how we're going to meet with the teams. But so either we'll meet together with teams, or I'll meet with one team and Sue will meet with another team, and then we'll switch back and forth the next week, that kind of thing. So anyway, so you guys are going to do a project. So Sue, do you want to say any more about this?
Yes, I expect you to find a team member, team of 5, and discuss about go over the list of topics and choose the topics from the list. And you're going to work on this project throughout the semester. And then also, I understand that there's an issue with the Discord server link. I'm going to update during the break so that you guys can join the Discord server. So make sure you join the Discord server by today. Oh, okay, then I'll let you know. After this class, please, look for a team member, team of 5. So we have 65 students, I expect to have 17 teams. So after you form a team, and let me know who are the team members, so that I'll create a team. And then you're going to work with your team members throughout the semester. And then, after you find the team, and, actually, this course is a really good place to find a team member. So by next week, I want you to find a team member, and then by the following week, I want you to take the topic that you're going to work on. Are we good? Any questions?
Can more than one group work on the same topic or just do you?
Oh, it's okay, more than one group can work on the same, topic. That's okay, by guys going to each other. And also, besides the project, also we have one more item that we're going to do. We're going to have a quiz at the end of each class. So quiz is going to be the first in each class. A quiz, so make sure please bring your laptop. And then a quiz also is based on the video that we watched from the previous week. So then make sure you watch all the videos and aware what has been discussed in the video. And then we will have quiz following. So on the next week, we are going to have a quiz based on the contents that we discussed today. So then make sure that you watch this video very carefully, because we are going to have a quiz and a release, and that is going to be 30% of your grade. 30% of your grade is from quiz, 30% of your grade is from project, and 30% is from your video, and 10% is from your attendance. Any questions? Any questions? Oh, Professor, would it be okay if we get a 10-minute break so that I can update the Discord server link so students can join, make sure students can join the Discord server?
Professor, is it all right if we take a 10-minute break here?
One more thing before this. Okay, so Sue, you done?
Oh, yes, I'm done.
Okay, so one more thing before we take a break. The way the class will be organized is that the first half of the class, before the break, we'll talk about the material that you worked on during the preceding week. So if anyone wants to show their video, we can do that. Or we'll just review that material if you have questions about it and so on. And at the end of that time, before the break, we'll have a quiz. So, that should get you ready for that quiz. So you should have been thinking about that stuff all week and making a video about it, and then you should be able to do reasonably well on the quiz. Then we'll have a break, and after the break, we'll look at material for the coming week, which will mainly, again, be videos. So we'll go through whatever videos, I have lined up, and we'll do it the same way. I'll show you the videos and I'll interrupt so that it's really awkward and, talk about the hard parts if there are stuff and so on. And then you can go off and do your videos. Okay, so that's the way the class will be organized. And so let's take a break, and then we'll talk about the material, the actual material for this week.
7.3, we will have 16 minutes break, so that we are going to resume at 7:38, 7:40. We're going to make them at 7:40 at the end of the day. We will take our time at the end of the class, so make sure you're going to do this always. We're going to have a Q&A. All right, okay, so if you want to go back to that, let's go, if you go back to that. So let me.
That's very, very. Professor.
I actually, can I talk to you about the project?
Let me update the Discord server way
Sorry.
for everyone to join.
Yeah, that's good. Professor Lim, no quiz next week, right? Starting after. There's a, yeah, I know. There's a week here.
Hi, everyone. I updated the Discord server link. Would you please try to join the Discord server? Everyone, do you please join the Discord server?
Professor Abbott, would you say something for me just to test?
Yes, hi.
Okay, perfect. All good?
Be ready for the next half, second half.
Go ahead, Professor Abbott.
Okay. So we're going to look at two videos. One is Grant Sanderson's, one is a neural net, and the other is the universal approximation theorem. They're both nice videos. Together, they're almost an hour, so if I interrupt, we probably won't get through all of it, but obviously you can look at it afterwards. So let's get started with this. This is Sanderson's What is a Neural Net?
Sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this, and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future. But what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing, not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network, quote unquote, learning. This video is just going to be devoted to the structure component of that, and the following one is going to tackle learning. What we're going to do is put together a neural network that can learn to recognize handwritten digits. This is a somewhat classic example for introducing the topic. And I'm happy to stick with the status quo here, because at the end of the two videos, I want to point you to a couple good resources where you can learn more, and where you can download the code that does this and play with it on your own computer. There are many, many variants of neural networks, and in recent years, there's been sort of a boom in research towards these variants. But in these two introductory videos, you and I are just going to look at the simplest plain vanilla form with no added frills. This is kind of a necessary prerequisite for understanding any of the more powerful modern variants, and trust me, it still has plenty of complexity for us to wrap our minds around. But even in this simplest form, it can learn to recognize handwritten digits, which is a pretty cool thing for a computer to be able to do.
And at the same time, you'll see how it does fall short of a couple hopes that we might have for it. As the name suggests, neural networks are inspired by the brain. But let's break that down. What are the neurons, and in what sense are they linked together? Right now, when I say neuron, all I want you to think about is a thing that holds a number, specifically a number between 0 and 1. It's really not more than that. For example, the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network. Now jumping over to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again, some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons. And admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment. And 16, well, that was just a nice number to fit on the screen. In practice, there is a lot of room for experiment with a specific structure here. The way the network operates, activations in one layer determine the activations of the next layer. And of course, the heart of the network, as an information processing mechanism, comes down to exactly how those activations from one layer bring about activations in the next layer. It's meant to be loosely analogous to how in biological networks of neurons, some groups of neurons firing cause certain others to fire. Now, the network I'm showing here has already been trained to recognize digits, and let me show you what I mean by that. It means if you feed in an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents. And before jumping into the math for how one layer influences the next, or how training works, let's just talk about why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What is the best hope for what those middle layers might be doing? Well, when you or I recognize digits, we piece together various components. A 9 has a loop up top and a line on the right. An 8 also has a loop up top, but it's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now, in a perfect world, we might hope that each neuron in the second to last layer corresponds with one of these subcomponents. That anytime you feed in an image with, say, a loop up top, like a 9 or an 8, there's some specific neuron whose activation is going to be close to 1. And I don't mean this specific loop of pixels. The hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits. Of course, that just kicks the problem down the road, because how would you recognize these subcomponents or even learn what the right subcomponents should be? And I still haven't even talked about how one layer influences the next, but run with me on this one for a moment. Recognizing a loop can also break down into subproblems. One reasonable way to do this would be to first recognize the various little edges that make it up. Similarly, a long line, like the kind you might see in the digits 1 or 4 or 7, well, that's really just a long edge, or maybe you think of it as a certain pattern of several smaller edges. So maybe our hope is that each neuron in the second layer of the network corresponds with the various relevant little edges. Maybe when an image like this one comes in, it lights up all of the neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with the upper loop and a long vertical line. and those light up the neuron associated with a 9. Whether or not this is what our final network actually does is another question, one that I'll come back to once we see how to train the network. But this is a hope that we might have, a sort of goal with the layered structure like this. Moreover, you can imagine how being able to detect edges and patterns like this would be really useful for other image recognition tasks. And even beyond image recognition, there are all sorts of intelligent things you might want to do that break down into layers of abstraction. Parsing speech, for example, involves taking raw audio and picking out distinct sounds, which combine to make certain syllables, which combine to form words, which combine to make up phrases and more abstract thoughts, etc. But getting back to how any of this actually works, picture yourself right now designing how exactly the activations in one layer might determine the activations in the next. The goal is to have some mechanism that could conceivably combine pixels into edges, or edges into patterns, or patterns into digits. And to zoom in on one very specific example, let's say the hope is for one particular neuron in the second layer to pick up on whether or not the image has an edge in this region here. The question at hand is, what parameters should the network have? What dials and knobs should you be able to tweak so that it's expressive enough to potentially capture this pattern, or any other pixel pattern, or the pattern that several edges can make a loop, and other such things? Well, what we'll do is assign a weight to each one of the connections between our neuron and the neurons from the first layer. These weights are just numbers. Then take all of those activations from the first layer and compute their weighted sum according to these weights. I find it helpful to think of these weights as being organized into a little grid of their own, and I'm going to use green pixels to indicate positive weights and red pixels to indicate negative weights, where the brightness of that pixel is some loose depiction of the weight's value. Now, if we made the weights associated with almost all of the pixels 0, except for some positive weights in this region that we care about, then taking the weighted sum of all the pixel values really just amounts to adding up the values of the pixel just in the region that we care about. And if you really wanted to pick up on whether there's an edge here, what you might do is have some negative weights associated with the surrounding pixels. Then the sum is largest when those middle pixels are bright, but the surrounding pixels are darker. When you compute a weighted sum like this, you might come out with any number. But for this network, what we want is for activations to be some value between 0 and 1. So a common thing to do is to pump this weighted sum into some function that squishes the real number line into the range between 0 and 1. And a common function that does this is called the sigmoid function, also known as a logistic curve. Basically, very negative inputs end up close to 0, very positive inputs end up close to 1, and it just steadily increases around the input 0. So the activation of the neuron here is basically a measure of how positive the relevant weighted sum is. But maybe it's not that you want the neuron to light up when the weighted sum is bigger than 0. Maybe you only want it to be active when the sum is bigger than, say, 10. That is, you want some bias for it to be inactive. What we'll do then is just add in some other number, like -10, to this weighted sum before plugging it through the sigmoid squishification function. That additional number is called the bias. So the weights tell you what pixel pattern this neuron in the second layer is picking up on, and the bias tells you how high the weighted sum needs to be before the neuron starts getting meaningfully active. And that is just one neuron. Every other neuron in this layer is going to be connected to all 784 pixel neurons from the first layer. And each one of those 784 connections has its own weight associated with it. Also, each one has some bias, some other number that you add on to the weighted sum before squishing it with the sigmoid. And that's a lot to think about. With this hidden layer of 16 neurons, that's a total of 784 times 16 weights, along with 16 biases. And all of that is just the connections from the first layer to the second. The connections between the other layers also have a bunch of weights and biases associated with them. All said and done, this network has almost exactly 13,000 total weights and biases. 13,000 knobs and dials that can be tweaked and turned to make this network behave in different ways. So when we talk about learning, What that's referring to is getting the computer to find a valid setting for all of these many, many numbers so that it'll actually solve the problem at hand. One thought experiment that is at once fun and kind of horrifying is to imagine sitting down and setting all of these weights and biases by hand, purposefully tweaking the numbers so that the second layer picks up on edges, the third layer picks up on patterns, etc. I personally find this satisfying rather than just treating the network as a total black box, because when the network doesn't perform the way you anticipate, if you've built up a little bit of a relationship with what those weights and biases actually mean, you have a starting place for experimenting with how to change the structure to improve. Or when the network does work, but not for the reasons you might expect, digging into what the weights and biases are doing is a good way to challenge your assumptions and really expose the full space of possible solutions. By the way, the actual function here is a little cumbersome to write down, don't you think? So let me show you a more notationally compact way that these connections are represented. This is how you'd see it if you choose to read up more about neural networks. Organize all of the activations from one layer into a column as a vector. Then organize all of the weights as a matrix, where each row of that matrix corresponds to the connections between one layer and a particular neuron in the next layer. What that means is that taking the weighted sum of the activations in the first layer, according to these weights, corresponds to one of the terms in the matrix vector product of everything we have on the left here. By the way, so much of machine learning just comes down to having a good grasp of linear algebra. So for any of you who want a nice visual understanding for matrices and what matrix vector multiplication means, take a look at the series I did on linear algebra, especially chapter 3. Back to our expression, instead of talking about adding the bias to each one of these values independently, we represent it by organizing all those biases into a vector and adding the entire vector to the previous matrix vector product. Then
So let me just interrupt here, not going to say a whole lot, but I want to point out that the green stuff, the weights, and the blue stuff, the biases, after the neural net is trained, are constant, they're fixed. And the A's are the inputs, which vary with whatever the neural net is given as input. So he said earlier that there are about 13,000. If you look at the total number of weights and biases. So in large language models, you hear numbers such as 50 billion or 100 billion. 100 billion means there are 100 billion of these numbers. So when it says, how many parameters does your neural net have? And you get 100 billion, that's what they're talking about.
As a final step, I'll wrap a sigmoid around the outside here. And what that's supposed to represent is that you're going to apply the sigmoid function to each specific component of the resulting vector inside. So once you write down this weight matrix and these vectors as their own symbols, you can communicate the full transition of activations from one layer to the next in an extremely tight and neat little expression. And this makes the relevant code both a lot simpler and a lot faster, since many libraries optimize the heck out of matrix multiplication. Remember how earlier I said these neurons are simply things that hold numbers? Well, of course, the specific numbers that they hold depends on the image you feed in. So it's actually more accurate to think of each neuron as a function, one that takes in the outputs of all the neurons in the previous layer and spits out a number between 0 and 1. Really, the entire network is just a function, one that takes in 784 numbers as an input and spits out 10 numbers as an output. It's an absurdly complicated function, one that involves 13,000 parameters in the forms of these weights and biases that pick up on certain patterns, and which involves iterating many matrix vector products and the sigmoid squishification function. But it's just a function nonetheless. And in a way, it's kind of reassuring that it looks complicated. I mean, if it were any simpler, what hope would we have that it could take on the challenge of recognizing digits? And how does it take on that challenge? How does this network learn the appropriate weights and biases just by looking at data? Well, that's what I'll show in the next video. And I'll also dig a little more into what this particular network we're seeing is really doing. Now is the point, I suppose I should say, subscribe to stay notified about when that video or any new videos come out. But realistically, most of you don't actually receive notifications from YouTube, do you? Maybe more honestly, I should say subscribe so that the neural networks that underlie YouTube's recommendation algorithm are primed to believe that you want to see content from this channel get recommended to you. Anyway, stay posted for more. Thank you very much to everyone supporting these videos on Patreon. I've been a little slow to progress in the probability series this summer, but I'm jumping back into it after this project, so patrons, you can look out for updates there. To close things off here, I have with me Leisha Lee, who did her PhD work on the theoretical side of deep learning, and who currently works at a venture capital firm called Amplify Partners, who kindly provided some of the funding for this video. So, Leisha, one thing I think we should quickly bring up is this sigmoid function. As I understand it, early networks use this to squish the relevant weighted sum into that interval between 0 and 1, kind of motivated by this biological analogy of neurons either being inactive or active.
Exactly.
But relatively few modern networks actually use sigmoid anymore.
Yeah.
That's kind of old school, right?
Yeah, or ReLU seems to be much easier to train.
And ReLU stands for rectified linear unit.
Yes, it's this kind of function where you're just taking a max of 0 and A, where A is given by what you were explaining in the video. And what this was sort of motivated from, I think, was partially by a biological analogy with how neurons would either be activated or not. And so if it passes a certain threshold, it would be the identity function. But if it did not, then it would just not be activated, so be 0. So it's kind of a simplification. Using sigmoids didn't help training, or it was very difficult to train at some point, and people just tried ReLU, and it happened to work very well for these incredibly deep neural networks.
All right, thank you, Leisha.
Okay, one other thing I want to point out. Let me get there. Okay, this product of weights and activation values. If you look at it, it's a vector inner product. So if the W's are one vector, in this case, a row and a matrix, and the A's are another vector, in this case, a column matrix, and you take the inner product of them, what you get is this times that plus this times that, and so on. So this operation you can think of as the inner product of two vectors. Now, that's important because this kind of action, the inner product action, is done over and over and over and over again in neural nets. Now, what is a GPU? A GPU is something that can do this kind of thing in parallel very quickly. And NVIDIA, the company that makes all the fancy GPUs, makes things like that. So that's why NVIDIA is such a big deal, because it makes chips that do inner products very well in parallel, and lots of them at the same time. Okay, so let's go on to the next one. The universal approximation theorem.
If you have worked in machine learning, you may have heard of this. Otherwise, you may be hearing about this theorem for the first time. This lecture is an attempt to illustratively prove this theorem. And my understanding is that if you truly understand universal approximation theorem, you have a very good intuition for why machine learning or neural networks are able to do such powerful things that it is capable of doing. So technically, this is not in the strict sense, this is a proof, but this is more like an illustrative demonstration or a way for you to be convinced of the validity of this theorem. So my name is Dr. Sridhar Panat. I'm a PhD from MIT. And in this lecture, we'll be going through this theorem with a very specific example. So let's get into the lecture. Universal approximation theorem states that a feed-forward neural network with just a single hidden layer, and this single hidden layer will just have finite number of neurons or nodes, and this kind of a neural network can approximate any continuous function within
a range or a subset of input values. So this function will have set of inputs, but a neural network, which is of feed-forward nature and single hidden layer and finite number of neurons in this hidden layer, can approximate any continuous function within a subset of inputs to any degree of accuracy, provided the activation function that we use in this feed-forward neural network is non-constant, it is continuous, and it is bounded. There are so many different terms here, and that's the reason why I have made most of them, or most of the important ones, in bold and underline: feed-forward neural network, single hidden layer, finite number of neurons, etc. So don't be overwhelmed if you cannot visualize this theorem really well. Basically, in simple sense, what it is saying is, using discrete set of items, you can kind of approximate a continuous function or anything that is continuous, and the degree of accuracy will depend on how many discrete items you are chopping this whole thing into. You may be familiar with this idea if you have done integration, numerical integration, as you can see in this picture. But what the universal approximation theorem is saying essentially is something like this. You can think of neural network as function approximators. And let's see if this is true. Let's see by taking a very specific example. So universal approximation theorem has been stated by many people, and this is Ian J. Goodfellow. He was formerly at Stanford and DeepMind, and he is a very, very big name in the machine learning community. And he also has stated that a feed-forward neural network with a single layer is sufficient to represent any function. And by any function here, it largely means continuous functions. The size of the layer may become infeasibly large if the function is very complex, and it may fail to learn and generalize correctly if the size is very small. But basically, this a feed-forward neural network with a single layer is sufficient to represent any function. And there are many famous such codes, but our goal is to try to understand the intuition that all of these people had when they were stating this theorem. So let us consider this continuous function. This is a very simple function, y equal to x cubed minus 3x squared plus 2x plus 5, like a cubic equation, basically. And here we have plotted the range from x equal to -2 to x equal to 4. That's the range we have plotted. And y looks like it approximately goes from -20 to +30, roughly. So we can, if we consider these set of straight lines, so these are a bunch of straight lines, red, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have made 11 straight lines. Some of them are solid lines, some of them are black dotted lines. And if we overlay this on top of the function that we saw earlier, we can see that these lines, these set of lines, approximate the function very well, as if it's like a piecewise linear function. And the more the number of such lines, or the more the number of divisions to which we've chopped the range of this function, the x range of function, the better and better this piecewise linear approximation will become, right? So this is obvious to see, and you can also already imagine this. This is not at all something that is surprising. Now the question is, how can we mathematically represent these lines? This is a very tricky question. It's not trivial. You may think that, okay, I can easily calculate the equation of each of these straight lines piecewise individually, and I can represent my whole function as a piecewise function. But let's say I don't want to represent it as a piecewise function, because in piecewise linear functions, the equation of this line is y equal to, let's say, 0x plus 5. And the equation of this line may be y equal to something else. But it's valid only in that range. So here, y equal to 0x plus 5 is only valid in the range of x equal to 0 to x equal to 1. Outside of that, it is not valid. But I want to be able to write a function where I don't have to look at the range within this current range that I'm looking at. So currently I'm looking at -2 to 4. I don't want to chop it up any further when I'm defining my function, right? I want a function that can look like something like this, or any other function, any other continuous function. And I don't want to use a piecewise linear function, although the outcome may look like a piecewise linear function. If you are not clear what this means, I'll show you in a moment. So consider this very fascinating yet simple function, ReLU, rectified linear unit. You may have heard of this already if you're familiar with machine learning and neural networks. And ReLU is nothing but ReLU of x is max of 0, x. So what does this mean? If x is positive, the max of 0, that positive number is x itself. So if x is greater than 0, the value of the function is y equal to x. What if x is less than 0? That means max of 0, any negative number is 0 itself. That is the maximum value, which means the value of ReLU of x would be 0 for all negative numbers, and it will be x itself for all positive numbers. So this is a simple version of the ReLU function. Now there are many different types of the same ReLU function that we can construct by modifying the sign of the ReLU function or adding like a constant to the x. Let's see how we can accomplish different types of ReLU functions using the basic same idea. So this is a platform called Desmos, and we can plot any kind of functions here to visualize them. I'll be sharing the link to this in the description. So I highly recommend you to check this out. So this is the normal ReLU function. So here I have defined F1, F2, F3, etc. up to F6 different functions, but I'm only plotting one of them, which is the normal ReLU function here. And you can see that for x less than 0, it's the value is 0. For x greater than 0, the value of y equal to x. Now, can you look at this? Let's say y equal to ReLU of x minus 1. Then what that means is for all the values from negative infinity till x equal to 1, the ReLU, the value of this is 0, which is, as you can see by seeing this red line. And for all value of x greater than 1, the ReLU is basically x minus 1. So if x is 2, the value of this function f1 is 2 minus 1 equal to 1. So this is like a ReLU that is offset by 1 unit to the right side, right? Now, what if I visualize this f3? F3 is ReLU of x plus 1. So ReLU of x plus 1 is nothing but the original ReLU offset by minus 1 in the negative x-axis direction. This is fairly easy to understand, I hope. Okay, let's look at y equal to 2 times ReLU of x plus 1. So now what will happen? The ReLU of x plus 1 was this purple kind of line. The slope of that in the values where the y-axis value is positive will become double, because now the function is 2 times ReLU of x plus 1. That's why this orange line will have twice the slope of this purple line. How about minus ReLU of x? So ReLU of x is this green line, right? And minus ReLU of x will be like a mirror image of that, where the x-axis will act as the mirror. So for all negative values of x, the value of this will be 0. For all positive value of x, the value of negative of ReLU of x will be minus x. What about this? Minus 3 times ReLU of x plus 2. So this will be the normal ReLU. It will be offset by minus 2 in the x-axis, so negative axis direction. And the slope will be minus 3. So this slope is actually minus 3. So it's not, so if I keep it as minus 1, then you can see that the slope is minus 1. If I keep it minus 0.5, slope is again increasing. It's basically going in the magnitude is decreasing, but the value is increasing. And if this is 0.5, then the slope will be, if this is plus 0.5, slope will be positive and its magnitude will be 0.5. So this is how we can manipulate the constant outside of ReLU and the numbers associated with the x. And we can get different types of ReLU. We can shift it, we can flip it downward. We can also have ReLU whose definition is something like this, ReLU of minus x. So let's plot that. What about this? ReLU of minus x. How would this look like? Let me not plot anything else. ReLU of minus x is exact. You can see that it's a mirror image of ReLU of x, but this time the mirror is not x-axis, the mirror is y-axis. Right? So, and what if now it is minus x plus 2? X plus 2. Then what happens is you are now shifting 2 units to the right. If it is minus x minus 2, it will be shifted to the negative side. So there are so many different functions that we can construct using this simple combination of linear functions. ReLU is essentially linear in its positive range, but zero in its negative input range. But using this, we can construct so many different types of piecewise linear functions. So now what we will see is, for the function that we were considering, we can see how to construct combinations using these ReLU. So what we want to first try is, let's try to add and subtract the ReLUs to see what is the result that we can get out of it. So can we add some 2 or 3 different ReLUs to see if we can get some other shapes which are not really possible using normal functions? Let's see that. So have a look at maybe just these 2 functions. Okay, let's take ReLU of x. So this green function is ReLU of x. And let's also take maybe ReLU of -x plus 2. And what we could do is we can define a 7th function, f7 of x. f7 of x equal to maybe I can say that this is f5 of x plus f6 of x. We can see what this looks like. This may not look like much. If there are spaces over here, it will not work. So I have to delete any white spaces. Yeah. And there is a white space here. Okay. So now you can see that the function looks something like this. The slope is completely negative in this range. In fact, it's always negative, the slope of this function. We can also do something like, so you see this one, this function this triangle-like structure which I got. I can open this and I can have a look at it. So here, let me first not display anything. First, let me display just the normal ReLU. So this is the normal ReLU function. And if I shift the ReLU by 2 units to the negative axis, x-axis, it will look like this. If I have another ReLU, which is -2 times ReLU of x minus 2, it means the point where the value of the function transitions will be x equal to +2, and the slope will be -2. So then this green line is the f2 function. And now f3 equal to f1 plus f2 will be nothing but this black color. So let me mask everything else. You can see that here we are now even able to create this triangle-like function. And this shape is coming purely as a result of combination of 2 different ReLU functions. So this is how we can use combination of ReLU functions to create whatever we want. So far, I have not showed whatever. I'm just showing a simple structure, simple function here. But now let's come back to our example, because our example was a complex function, right? It was a cubic equation. Let's see how we can approximate that cubic equation using bunch of ReLU functions. So we have a cubic equation which can also be represented using these piecewise linear functions. So if somehow these piecewise linear functions could be created using a set of ReLU functions, that would be awesome, because then ReLU, as you know, are used as activation functions in neural networks, which means this whole function we can potentially represent using neural network. So we will see how to do that. So first, let us try to find the ReLUs that make up this function, right? So let's see that. So let us plot the function that we are looking at first. This is x cubed minus 3x squared plus 2x plus 5. So this was the original function that we were trying to approximate, x cubed minus 3x squared plus 2x plus 5. And let us plot like a normal ReLU first. This is how a normal ReLU looks like. And you might think that the axis, the tangent or the slope is not 45 degrees, but it's actually slope is 1, because here the y-axis range is from -20 to 30, but x-axis range is only from -3 to 5 in this particular case. So that's why it appears as though the slope is not 1, but in fact it's 1. Okay, so clearly this ReLU is not sufficient to do anything. So let's add another one. Maybe I can define something like this. Let's say f1 of x equal to, so I want to shift the ReLU to the left till such that the transition point is from -2 2 minus 1. So how do I shift the ReLU to negative direction? I can say I'll use capital R. So it's capital R of x plus 2, right? Okay, now the ReLU shifted to -2, but the slope is still not good enough. So maybe what I can do is, let's say the slope, I want to keep the slope to be similar to whatever the slope of this guy is. So the slope of this guy is when the x is changing by 1, the y is changing by 20. So I would say the slope is 20. So maybe here I'll multiply this by 20. Now, what's the problem here? This is not really the ReLU that we are looking for. So what I can do is I can define f maybe final. So I'll just say f final equal to minus f final of x equal to minus f1 of x. I'll tell you why we are doing this. So f final of x equal to minus f1 of x. I am not sure if this is being displayed right now because there are some empty spaces. Okay. One more thing that I can do here is, let's say, okay. Probably what I should do is, like, instead of this blue line, I should shift the blue here and make the slope to be like this, right? So minus x, what if I had something like this? Minus x minus 2 or minus 1, and the slope was minus 20. How about this? Then this part is approximating the function really well, right? So this looks good. The transition is happening at -1, and there is a straight line over here. I can also use 2 ReLUs here instead of 1 ReLU, but for now this looks fine. Okay. Okay, let me also define another new ReLU function, f2 of x equal to, now this time I want the transition to happen at x equal to maybe 0. So, and the slope I want to be, the x value is changing by roughly 1 and y value is changing by 5. So the slope could be 5, right? So I'll copy this, paste it here. And what I will do is this will be 5 and this will be just like that. So this is the pink ReLU, but the problem here is I should not have, actually I should just have a ReLU with plus x, plus 1, and slope is plus 5, and this can represent really well. Now let me see f final equal to f1 plus f1 of x plus f2 of x. What if I display only f final? Do you think I'm able to approximate? Let me also change the color so that you can see it properly. So the green is my final approximation, final meaning from the range -2 till 0. So this green line is now representing my original x cube minus 3x square plus 2x from this range of x equal to -2 till x equal to 0. Okay, now let's come back to our business. So we have, if we just look at the function, now our next transition is happening at x equal to 0, right? So our f, the final f is now looking like something like this. Let me see, final f is looking something like this. And I want the slope now to be roughly, so this one has how much slope? X is going from 0 to 1 and y is going from 5 to 10. So the slope of this part is 5. So I want to add something with slope maybe -5 so that I can kind of negate this part and create something with slope close to 0. So what I will do is I'll define a function f3 of x equal to -5 times ReLU of what? It should be x -1 because I want to shift the ReLU. I want to shift the transition point from, actually it should be transition point should be at x equal to 0 itself, I guess. So let me put it this way, and let me give it a green color, sorry, different color other than green, so that it looks different to you. So it could be blue color. Done. And now if I define the f final as f1 plus f2 plus f3 of x, f3 of x, you can see that now the green line is very nicely approximating. Let me block this blue. Now this green line is approximating this curve very well from -2 all the way till, even I would say it's even approximating till +2. Somewhat. I'm not saying it's exact, but to great extent, because we are only using so many divisions. If we divide it even further, it will be good. Okay, now what should happen to this green line? The green line has slope 0 right now. Its slope from the point of this x equal to 2, it should transition from a slope of 0 to, how much is this? X is changing by 1 and y is changing by 5. So again, the slope should become 5. So what can I do? I will define a function f4 of x, where f4 of x equal to, what should be my slope? Slope should be 5, right? 5 times r of what should x plus, it should be x plus 2. Sorry, x minus 2. So that the thing is shifting all the way till the transition point happens at x equal to +2. So now this is this white line, and let us add this onto our final. So now f final will be this plus f4 of x. You see, it's beautifully representing now. I'll hide the white line now. Now the approximation is going reasonably well till x equal to 3. Now we are covered from x equal to -2 all the way till x equal to +3. Now let us try to approximate from x equal to +3 all the way till x equal to something like, I think the range here is, let's try till x equal to +4. I only care from -2 to +4. So here the x value is changing by 1, but the y value is changing by how much? 10 plus 10, roughly 20. So the slope here should change from, currently the slope is 5 here, it should change from 5 to 20, which means the slope of the new line that is added after this transition point of 3 should be an addition of 15, right? 5 plus 15 is 20. So if I add a new function called f5 of x, and if the slope of this is 15 times ReLU of, and where is the transition point? Transition point is at x equal to 3, so this will be x minus 3. Then if I add the f5 over here, so plus f5 of x. Now we have the new green line, and let me hide this blue line. Now you see the function is approximated reasonably well. So if I hide my original function, now this looks roughly like my original function, which was x cubed minus 3x squared plus 2x plus 5. And of course, I'm not approximating really well here, but obviously, as you can see, I have not used that many straight lines. I have only used very little number of straight lines. But as you can see, it's approximating really, really well. But one thing to note here, in my consideration, I only considered the x range from -2 till +4, -2 till +4. So if you zoom out, this approximation will not be good for outside that range. So outside this range means less than -2 or greater than +4. There will be significant diversion between this green approximated line, which is the sum of ReLUs, and this orange line, which is the actual function. Now let us do one more thing. In actual neural networks, when we write ReLU, we are doing ReLU of, let's say, wx plus b. So we won't have something like -20. Let's say we don't want this -20 or this business outside. We just want it to be ReLU of something, right? Minus ReLU of something else. So we just want addition and subtraction of ReLUs, or we can also write it just exactly like this, no problem. So I can show you how to represent this whole thing. We have 1, 2, 3, 4, 5 functions here. I can show you how to represent these 5 ReLU functions, which is operating to create this final function called f final, how this whole thing forms a neural network. So firstly, let us write this down. Let's get back to our PPT. So we got our ReLU function, find the ReLU that makes up our function. Let me write it down so that you also have the reference when we are referring to it again. So f final equal to, and this is a function of x, obviously. It's equal to f1, which is -20 times ReLU I'll just denote by R just to save some space. R of minus x minus 1, right? Then it is plus 5 times ReLU of x plus 1. Then minus 5 times ReLU of x. Plus 5 times ReLU of x minus 2. And plus 15 times ReLU of x minus 3. Plus 15 times ReLU of x minus 3. So now the range in which this is valid is from x belonging to minus 2 to plus 4. And that too, when I say valid, I don't mean to say that this is perfectly approximating our original function. I'm just saying that the extent to which we were happy. So this is the range in which we will be generally happy if this function was applied. So this is how we can use a bunch of ReLU functions to represent a complex function, or rather a complex continuous function. So how does the neural network look like now? The input is x. So the x is coming into the input node. There is only one input node because there is only one number as the input. There will be 5 nodes in the only one and only hidden layer. Now, what will be the values here? So the values, we can go back to our function. So the first node has minus 20 times ReLU of minus x minus 1. So minus x meaning this, the weight over here is minus 1 because it's minus x, and minus 1 is the bias. So this is the bias to the first node, that is minus 1. Then to the second node, it will be, let me just make this small. Second one, it will be 5 times ReLU of x plus 1. So you might be wondering, where is this minus 20 and where is this 5? I'll show you that in a moment. So here it is basically ReLU of x plus 1. So x plus 1 means the weight corresponding to that is 1, right? Weight is 1, and plus 1 means bias is also plus 1. So that will be here. So this arrow is a bias, so don't get confused. It's not something that is going from this node to this node. It's just a bias that is going into the second node. Then we have the third function, which is minus 5 times ReLU of x. So here weight is 1 and bias is 0. Then we have 5 times ReLU of x minus 2. So weight is 1 and bias is minus 2. So weight is 1 and bias is minus 2. Then we have 15 times ReLU of x minus 3. So weight is 1 and bias is minus 3. Weight is 1 and bias is minus 3. Now, what about these connections? The weights of these are the coefficients of our ReLU function. So first one is minus 20. Then here it is 5. Here it is minus 5. Plus 5. And 15. Now, can we write this neural network in a functional format? Of course. So here this tilde icon, I'm just showing it to represent our activation function. Obviously, our activation function is ReLU, right? So what would be the output that is coming over here? It will be ReLU of minus x minus 1, correct? Minus x minus 1. What about the output of here? That will be ReLU of plus x plus 1. So first one is minus x minus 1. Second is x plus 1. So this one would be, sorry, not that. Before we apply this, the output that is coming out here will be ReLU of x plus 1. What about this one? This one would be just ReLU of x, right? So I'll just draw it here. This will be just ReLU of x. Then this guy would be just ReLU of x minus 2, correct? Yeah, ReLU of x minus 2. X minus 2. So please don't get confused. I think I'm confusing you by using different notation. So when I say RE, I just mean ReLU. I don't mean real number or anything. So just please don't get confused. Then the final one would be ReLU of x minus 3, this one. So ReLU of x minus 3. I think that is what it's here also. Now, what happens here in this summation? What happens is this thing gets multiplied by minus 20. Then this thing will get multiplied by 5. This will get multiplied by minus 5. This will get multiplied by 5 and this by 15. And then you will add all of that. So what is the result? So minus 20 times ReLU of minus x minus 1. So approximation of f of x, maybe f approx is equal to minus 20 times ReLU of minus x minus 1 plus, what is this? 5 times ReLU of, this is this guy, right? 5 times ReLU of x plus 1. Then we have minus 5 times ReLU of x. Then we have 5 times ReLU of x minus 2 plus 5 times ReLU of x minus 2. I'm so sorry for using R and RE, but please consider that they are both the same thing. I'm just making this mistake while writing. Then plus 15 times ReLU of x minus 3. Is this our function that we had? We had minus 20 times ReLU of minus x minus 1. That is here, this one, this guy. Then 5 times ReLU of x plus 1. We had that, 5 times ReLU of x plus 1, right? This guy. Then we have minus 5 times ReLU of x. We have that here. So minus 5 times ReLU of x. Then we have 5 times ReLU of x minus 2. That is this guy. Then 15 times ReLU of x minus 3. That is this guy. So now what you really see is this neural network with these weights and these biases, and ReLU as the activation function can actually approximate what we have, the continuous function that we originally selected. The function was minus, it's here in this x cube minus 3x square plus 2x plus 5. These set of ReLU functions, if we add it up, it can very well approximate our function. Of course, as I mentioned earlier, if you want better accuracy or more precision, you can add more ReLU functions. You can chop up the function into more and more discrete pieces. So let us go back. Did we really demonstrate the universal approximation theorem here? The universal approximation theorem states that a feed-forward neural network with a single hidden layer containing finite number of neurons can approximate any continuous function on a subset of inputs to any desired degree of accuracy, provided the activation function is non-constant, bounded, and continuous. Did we satisfy these things? It's very now it does not look very complex anymore, right? So we had a feed-forward neural network, right? It was feed-forward purely, correct? We had a single hidden layer, right? Then we had finite number of neurons. How many did we have? We had 5 in the hidden layer. We had a continuous function. It was x cube minus 3x square plus something plus 5, right? That was a continuous function. And we had non-constant, bounded, and continuous activation function. What do we mean by bounded here? The boundaries are from -2 to +4 in our case. Non-constant, obviously, because we are using ReLU. ReLU is not constant. Is it continuous? Of course, it is continuous. So we have satisfied all these conditions. And now we are able to approximate the function that we originally selected. So let me just write it down here so that you know the feed-forward neural network part was correct. Single hidden layers. So in a number of hidden layers was 1, 5 nodes within the input layer. Continuous function. Yes, it was a continuous function. X cube minus 3x square. This was the function, right? Square plus 2x plus 5. So this is a continuous function, and we were using ReLU activation functions to get the approximation. So this wonderfully shows how we can demonstrate the actual universal approximation theorem using a very simple example. So when does the universal approximation theorem, when does it not work? So as you saw, it works only in a defined range of input. So what do we mean by defined range of input? In our case, it was from -2 to +4, right? X values from -2 to +4. And we saw that here. Here, between -2 to +4, this graph looks like good. The green color piecewise linear function is approximating our function really well. But if I zoom out, and if you can see more number of points from, let's say, a range of -10 to +10 or something like that, you can see that there is complete divergence. The green plot is not at all matching with our original function anymore. So the range has to be limited, or it has to be defined. We have to train the neural network to within the range. If a new range comes, the neural network has to be trained in that range to have good weights and biases. We may have to also increase the number of nodes in the hidden layer if we have to accommodate more range. And if there is a non-continuous function, we might need more than one hidden layer, correct? Okay, now one more thing before we conclude the lecture. Do you really understand the significance of activation function? Like, the reason why neural networks can approximate even these complex non-linear functions is because of the activation function. What happens if activation function was not there? Let's take a look at this, right? So let us go back to our graph. Let's say this was r of x equal to simply x. This was simply x instead of ReLU of x. Then what would happen if I just plot r of x equal to maybe max of x? Okay, I know why this issue is happening. It's because, oh yeah, sorry, it's not x, it's just z. R of z equal to z. And now do you see what's happening? I have added bunch of complex functions. These are all straight lines, right? Because r of minus x minus 1 is minus x minus 1. So these are all linear functions. And no matter whatever I do, if I add bunch of these linear functions together in whatever way we want by changing its slope, intercept, whatever, as long as it's a straight line, a combination of these straight lines will give me another straight line only. So if we don't have the ReLU activation function or any kind of activation function, we cannot represent nonlinear data using neural networks. This is why activation functions are so important. And I would even say it's the cornerstone of the whole idea of neural networks, that you can construct these piecewise functions and approximate pretty much any function that way. If you have discontinuous function, that is the reason why sometimes you have multiple hidden layers. So I hope this makes it very, very clear for you in a visual way, the importance of activation functions. And with that kind of insight, I think we can wrap up the lecture here. Thank you so much for listening. I hope this lecture brought some clarity into you, not just about universal approximation theorem, but also about the general concepts behind and general intuition behind the usage of neural networks. We'll be coming up with more lectures which are relevant to machine learning concepts from many different subsets of machine learning. So stay tuned to that. Until then, see you. So bye.
So wasn't that neat stuff? I thought that was cool that you could put all those things together. And the one thing I want you to notice besides the actual content were the two graphic systems. You know, the 3 blue, 1 brown graphic system was that Manum that Grant Sanderson created, and this one was whatever it was called, Desmond or whatever. I had it on the syllabus. And so those are really two nice systems you could use when you create your own videos. So thank you, perfect timing. We're just about done, and I'll see you next week.
Thank you.
Thank you, Professor.
Thank you.
The project in water.
Is that gonna be on this?